this is going on page 41 when we're done. So like I said, we have talked about limits as far as end behavior is concerned, but there's more to limits than just end behavior. And when we talk about limits, so I want you to look at this graph right here. I'm not going to talk about what this actually says right now, just look at the graph. When we talk about end behavior, and we're talking about as x approaches negative infinity, like this, and then x approaches infinity, right? Well, I can only approach negative infinity from the right side. I can't approach it from the left because I can't get on the other side of it, right? And same thing over here. I can only approach this from the left. I can't approach it from the right because I can't get on the other side of it. So we've really already looked at one-sided limits. We just didn't talk about it that way, but we can only get to those by one side. Actually, we'll never even get there, right? It's heading that way from one direction. So, but we do have from the left and from the right. So if you look at how this limit is written, this says the limit is x approaches c, and it has this little negative sign of f of x equals L1. And then this one has the little plus sign, kind of where the exponent goes. It's real tiny. So that means from the left and from the right, not going to the left and going to the right, from the left and from the right. So limit from the left, has a unique number and approaches c from the left. And then a limit from the right, a unique number as x approaches c. And then that says left again because I threw this together the last minute there. Right, should say right. I'm a victim of copying and pasting. Okay, so let's look at this actual function here from what it's asking me, because we're not asking about infinity. Okay, we're not talking about end behavior. This is more that middle behavior. As x approaches 2 from the left and as x approaches 2 from the right. All right, so as my x is approaching 2 from the left, what is the y value right over here? -1. And I'm approaching, I would think, by the way I'm approaching, that when I get to 2, I would still have that same y value, and I'd be approaching -1. Does that make sense? I'm approaching a y value of -1. If I approach from the right, there you go, my y value is 1. I'm approaching 2 from the right. Now my y value is approaching a +1, and it's different from the left and the right. What is the actual value of the function at 2? What's the value of the function right here at 2? Nothing. It doesn't exist, or it's undefined, right? So the function value itself is undefined, but the limit from the left is -1, from the right is 1. If I look at -2, what's the function value at -2? -1. And if I approach -2 from the left and -2 from the right, I'm approaching the same thing, and the limit would be -1. Okay? I'm going to show you a little short video about limits. I think it does a really good job of kind of explaining how limits work in general to help make all the rest of this stuff be super easy and make sense. So let's.
In a general sense, limits allow us to determine what value a function is approaching when we use a particular input. Not necessarily what the function gives us as an output, but rather what value it's getting arbitrarily close to. Let's explain limits using an analogy. Suppose you are watching TV and start getting a massive craving for pizza. Fortunately, you just happen to have some leftover pizza in the kitchen. So you get up from the couch and start heading towards the fridge. In this instance, if someone were to describe where you are going, they would say you are approaching the fridge. They would be confident in their description because as you keep walking, you are getting closer and closer to where the fridge is located. This example is the same thing we want to do with functions. When we take the limit of a function, we are describing where they are going. Let's see an example of this with the function 3x squared minus 1. For this function, I'm really curious what value the function is approaching as I use x values close to the number 2. Let's see this by using some inputs like 1.9, 1.99, and 1.999. When I use these, I get values such as 9.83, 10.8803, and 10.988003. From these values, it appears that the function is approaching 11. So we say that the limit of the function as x approaches 2 is 11. Remember, what I'm really saying here is that we can get arbitrarily close to the number 11. I just have to pick values that are sufficiently close to 2 in order to do it. Now at this point you might be thinking, that's fantastic, but couldn't you have also found the limit simply by plugging 2 into the function? wouldn't that also give you 11? In this instance, the answer is yes. But the focus with the limit should be on what value it's approaching, and there are some functions where you simply can't plug in a number to find the limit. In other words, they are not always the same. Let's cover this by going back to our pizza analogy. Like before, you've been struck with a craving for pizza. So you are headed towards the fridge for a quick snack. Now, in one scenario, the fridge is there, loaded with pizza, and you can easily satisfy your craving for pepperoni. But in an alternate scenario, the fridge is gone, possibly stolen by pizza-craving ninjas, and you are left empty-handed. Even though both of these situations are completely different, your behavior leading up to them is exactly the same. In either case, you are still approaching the fridge. This is the key difference with limits. They are used to describe what value a function is approaching. They are not used to describe the value the function actually reaches. Let's see how this works with yet another function. Let's go ahead and use x squared minus 4 all divided by x minus 2. Like before, we are interested in what value the function approaches as we use x values close to 2. Let's go ahead and choose some inputs like 1.9, 1.99, and 1.999. When we use these, we get values of 3.9, 3.99, and 3.999. From these, it appears that the function is approaching 4. So again, we say that the limit of the function as x approaches 2 is 4. If you try and find this value by instead plugging in 2, something strange happens. When you plug 2 into the function, you get 0 divided by 0. This shows that the function doesn't actually ever get to 4. In fact, a quick look at the graph shows a hole right where 4 is. Despite the hole, the behavior of the function leading up to it is the same. Since the behavior is the same, we still say that the limit of the function as x approaches 2 is 4, even though it never actually gets there. Hopefully both of these examples really highlight how limits focus on the behavior of a function, what they get arbitrarily close to. One thing we still have left to cover is what it exactly means when we say that a function gets arbitrarily close to a value. But don't worry, we'll be able to tackle that tricky problem in the next video when we introduce epsilon and delta. Thanks for watching. Hey, did you enjoy this video?
So we're not introducing epsilon and delta, but so the point of all of that right now is that you're approaching it. You don't have to actually get there. You might need to remind yourself of the pizza craving ninjas that it's okay, we can't actually make it there. Sometimes the limit and the function value are the same, sometimes they're not, okay? It just depends on how it works out for you. All right, so I have here a bunch of functions. We're going to evaluate these limits from the left and from the right, but we're going to do it graphically. Instead of giving you a huge packet of notes with a ton of graphs that would have taken like a ton of paper, I have these graphs in Desmos. I'm going to assign these notes to you as an activity, or I don't know if it all has the same word in Desmos. I don't know. You don't have to go do anything with it, but if you need to go back to your notes and you look at number 4 and you don't, we have answers there, but you have no graph, then it's not going to make any sense to you. So you can just go back in there and look at number 4 on that. You could also type them in yourself, but I know that you may not know how to type in the piecewise functions and things like that. So if you need to go back and look at graphs, you'll be able to see these as well. So this first graph, which I already have graphed, we're going to look at the limit as x approaches -3 from the left and from the right. That's this one right here. So we're going to look at as x approaches, as x approaches -3 right here from the left. So as x approaches -3 from the left, what is the function approaching? -2. -2. I'm approaching -2, right? As I approach -3 from the right, I'm approaching what? -7. So it's -2 and -7. Does that make sense? So my answers here, the limit as we approach from the left is -2, from the right, -7. It's that easy, okay? The next one, we're going to look at 0 as we approach 0 from the left and 0 from the right. So as we approach 0 from the left, what is the function approaching? 1. As we approach from the right, then it's -5. You agree with that? 1 and negative 5. Then this next one is going to be as we approach negative 2 from the left and the right. So this is similar to that one that's up on the top of your paper. These little vertical lines here, it's just some glitch in how, I don't know why they're there on some of these and not on others, but that doesn't really exist, then it wouldn't be a function, right? So you just kind of have to ignore those. All right, so as we approach negative 2 from the left, what's the function approaching? Negative 5. As we approach negative 2 from the right, we're approaching 5. Okay, so it's negative 5 and 5. Any questions at this point? Okay, if you're thinking this seems way too easy, it's okay, you're probably doing it right because it is just pretty straightforward. Okay, so then as we approach negative, or is that 1 or negative 1? As we approach 1 from the left and the right, so as I approach 1 from the left, what's my function approaching? Infinity. And as we approach 1 from the right, it's approaching negative infinity. Infinity and negative infinity. Okay. Alrighty. And then as x approaches negative 4 from the left and right. Okay, so negative 4 is right here. So as I approach negative 4 from the left, I'm going to where? Negative infinity. As I approach negative 4 from the right, positive infinity. Negative infinity, infinity. All right, and then secant of x. That's not a function I expect you to be familiar with, but honestly, the rest of them you weren't really familiar with them either, right? Secant is the reciprocal of cosine. Cosine should sound familiar from geometry. These are not graphs that we have graphed yet. We will get there, but I went ahead and left this one on here. I want the limit as x approaches pi halves from the left and from the right. So this is what your secant graph looks like. Okay, and I even changed this so it was in terms of pi's. So here's pi halves. Looks like an asymptote to me. So as I approach pi halves from the left, what's my function approaching? Infinity. As I approach from the right, I'm approaching negative infinity. So see, you don't have to understand the graphs. Infinity and negative infinity. Okay, everybody okay with that? Now, for a limit to exist, right, the existence of a limit, because sometimes my answer is does not exist. For a limit to exist, so it said two-sided limit exists if and only if both the left and right limits exist and are equal. So if I have the limit, notice this says the limit as x approaches c, and it doesn't say from the left or right, just as I approach c, it exists if and only if the limit from the left and the right are equal to each other. So if you look back up here, without us even looking at the graphs again, I can tell you that on number 1, the limit as x approaches negative 3 does not exist because the limit from the left and the limit from the right, they both exist, but they're not the same because we were approaching two different things. Does that make sense? So in order for it to exist, you have to approach the same thing. So honestly, none of these approach the same thing, right? So the overall limit that's not from the left or the right of all of these just wouldn't exist. Okay, so now we're going to look at some where it's kind of all mixed up. Some are asked from the left, some are asked from the right, some are just asked overall. So when you look at number 7, it says the limit as x approaches 2. So I still have to check from the left and the right and see if they're meeting at the same place. And if they are, even if we don't actually get there, if they're heading towards the same place, then my limit can exist. So for number 7, the limit as x approaches 2. All right, so here's 2, right? As I approach 2 from the left and as I approach 2 from the right, am I heading towards the same spot? Yes, so the limit exists. I just have to figure out what it is, right? And if I actually go to 2, you can see, I don't know why that's popped up, sorry. If I can actually get there. At 2, it's actually undefined, right? But what would the limit be? Where am I headed towards? Negative 2, exactly. So then on number 8, I'm asked for the limit as x approaches negative 1 from which direction? Which is which direction? The right, good. And so as I approach negative 1 from the right, my function is approaching negative infinity. So then when I look at number 9, with the limit as x approaches -4, just -4 in general, so we've got to look at them from both directions. Okay, so here's -4 right here. If I'm going from the left and from the right, does it approach the same thing? As I approach it from the left and I approach it from the right, is it approaching the same thing? Yes. -4, your asymptote's at -3. Just because you have an asymptote doesn't mean that's what we're using. This is as x approaches -4, which is right here. So as I approach -4 from the left, and as I approach -4 from the right, then I am approaching what? 4. All right, so then the next one, the limit as x approaches 3. So I have to look at the left and the right again. So here's 3, right? Is 3 my asymptote? Yes, as I approach from the left, it's going to -infinity. As I approach from the right, it's going to a positive infinity. Are those the same thing? No, they are not. So your answer is does not exist. Okay. Everybody okay with that? All right. So then we're going to look at approaching 0 from the left. As I approach 0 from the left, where is my function approaching? -infinity. All right, number 12, as x approaches 1. As x approaches 1. So as x approaches 1 from the left and from the right, are we approaching the same thing? Yes. What are we approaching? Positive infinity. Let's just pause here for just a second. We're approaching positive infinity from the left, positive infinity from the right. So the limit from the left and the limit from the right are the same. Let's think about what this said right here. Then we're just going to kind of put a pin in it. It said in order for our limit to exist, the limit from the left has to equal the limit from the right. Does infinity equal infinity? Is infinity a number? Then it can't equal anything, right? So technically, this is not true, but our answer is still infinity. Put a pin in that. We're going to come back to that, but I want you to think about that for a second. All right. Then we're going to look at number 13. The limit as x approaches 0 from the right. So as we approach 0 from the right, what are we approaching? From the right? From the right, yeah. From the right, positive infinity. So you might have to say to yourself from the right because it's not going to the right, coming from the right. All right, then the limit as x approaches 0 for 14, so it has to be the same from both sides. As I approach 0 from either side, are they the same? No. So what's my answer? D and E. Okay. Then the next one, you're approaching 5 from the left. Is that a minus? Mine's just a blur. Okay. Minus 5 or negative 5? 5 from the left. Okay, as I approach 5 from the left, what am I approaching? -1. Mm-hmm. All right, so then the limit as x approaches 1 for 16. All right, so as x approaches 1, from the left and from the right, are we approaching the same value? Yes. Okay, so we're approaching the same value, so it exists. Do we get to just guess off of our graph? No, we don't. Right now, we're really just looking at it graphically. This is going to take it a little bit deeper than we need to go right now, but it was mentioned in the video, so I left this on here. If I substitute in 1, it's going to be undefined. Okay, but if I substitute in numbers that are just a little bit less than 1 and a little bit more than 1, you can see when it's a little bit less, I get 0.500 something something. And if it's a little bit more, I get 0.4998. So what would be a reasonable number to actually go there? 0.5, exactly. And there's other ways to get it more specific, but like I said, right now I just want you to understand the concept, and then we'll go deeper into that stuff. All right, number 17, as x approaches -2. And so as I approach -2 from the left and from the right, am I approaching the same thing? No. So then my answer is does not exist. All right, so then the limit as x approaches -3 from the right. Okay, as I approach -3 from the right, what am I approaching? 0. As I approach -3 from the left, what am I approaching? 0. What's the function value at -3? 0. They're all three the same here. Not that it asked me for all of that, but my answer here is 0. Okay, so these next few are asking us about infinity. Okay, so we're doing specific numbers, kind of like middle behavior. We're back talking about the end behavior. When I look at number 19, I want the limit as x approaches -infinity. So as x approaches -infinity, what is my function approaching? 0, okay? And notice that if it's -infinity or positive infinity, it's still going to be 0, right? Even though right here, it dips down below 0. That makes absolutely no difference because we're talking about -infinity, right? So my answer is 0. The next one, we are approaching infinity. So as x approaches infinity, what is the function approaching? 0. All right, so then the next one is x approaches infinity. What do you think? -infinity. Let's look at the function, because I gave you not only a graph, but you can see what the equation is, plus it's on your paper. This is a rational function. Is it top heavy, bottom heavy, or tied in degree? Top heavy, which means no horizontal asymptote. Is this the right setup to have a slant asymptote? Yes, because it's just one greater in the numerator, right? So I have a slant asymptote, so you can kind of see where that is. Ooh, poop. Unless I gotta hit the wrong thing. Let me get back. What number are we on? 21. There we go. Okay, so you can see how you've got this slant asymptote coming in here, even though it's not actually drawn in there. So we are approaching -infinity. So if you have the equation and the graph, you can use what you know about asymptotes, and you don't have to look at the graph, or maybe you kind of need both of them. I don't know. Let's see, number 22. As x approaches infinity. All right, so as x approaches infinity, it's going to be a number, right? Do you think it's 0? No. What would it be? Top heavy, bottom heavy, or tied in degree? Yeah, it's tied in degree, so I would just take the ratio there and get 1/4. Okay, so it's almost 0, but it's 1/4 that I know for sure. If this was a situation where all you had was the graph, you'd have a much more obvious graph to know where it went. You wouldn't have to worry about guessing on that. Okay. All right, number 23, x approaches -infinity. So as x approaches -infinity, what do you think your function is approaching? -5. Okay, good job. That's a funky little graph there. -5. All right, and then last one before we talk when they fail to exist. We're going to look at as x approaches infinity. So as x approaches infinity, what does the function approach? Infinity. And look at this function that we have here. This is top heavy, but when we take the ratio of those leading terms, we get x squared, so the end behavior should model a quadratic, which it does, and your answer is infinity. All righty. Now, let's talk about when a limit can fail to exist. All right. And again, this is not really 100% of what we're talking about with limits here, but this stuff is going to come up, so I just wanted to talk about it all at once, so it won't just feel like I'm just throwing little random things at you. So if we contain, and on mine, this graph is hard to see. I don't know about on yours, but this is what the graph actually looks like here. Just in case you can't tell on yours, because you can't tell on mine. It was very similar to that first one that we looked at, except this one's solid here. So if we have a jump discontinuity, and that's what this is. If I put my pencil down and I start to trace along, I have to pick it up and jump up here to keep going. So it's a jump discontinuity. If I have that, then it's going to approach a different number from the left than from the right. And since it's different from the left and the right, that's why it fails to exist, but it's just straight up a jump discontinuity. What is the function? So the limit as x approaches 0 does not exist, and we can't say equals does not exist. I didn't catch those were there. It just does not exist. The limit doesn't exist, but what is the function value at 0? 2. Is it 2, right? I don't know how small yours is and how easy it is to see, but it's a positive 2. So the function value, it's positive 2 right there. All right, so the next time it fails to exist is when you have a vertical asymptote. There's your vertical asymptote right here. Did we just look at some that had vertical asymptotes? Yes. Did we say our answers were infinity and negative infinity? Yes, we did. That's not how we got infinity here, but that's how we got all these up here. It all had to do with vertical asymptotes. But remember, I told you, like I think it was on this one, where I'm not sure which one it was exactly, but they're heading to the same thing, and we say that the limit is infinity, but they can't really be equal, so it really doesn't exist. This is kind of why here. Technically, as I approach at -2 from the right, my function is approaching infinity. Technically, my answer to the limit would be does not exist. Okay. However, we didn't write that for any of them, and we're not going to. Because, and again, I'm going to mark out this equals. In this case, it doesn't exist. They're going to different places, right? That one totally makes sense. But even if they're going to the same or it's just one side, then technically it doesn't exist because of the vertical asymptote. But we are allowed to say infinity because because it's still important to know which direction it might be going. And so you could say, and it says here, increases or decreases without bound. So if I was asking as we approach -2 from the right, technically the answer is does not exist, approaches without bound. Coming from the left, does not exist, decreases without bound. But everybody agrees in the calculus world that that's ridiculous to write out every single time, and so it's okay just to say infinity. You with me on that? So it's one of those where it's technically wrong, but that's what we do it anyway. All right, and then the last time is when it oscillates. Now, we've looked at a couple. I mean, not that we've done a lot with it, but I've shown you some pictures where it might have oscillated like something like this. Then that's okay because we're still approaching 0 that way. But I'm sorry, yeah, the function's approaching 0. But if I want to know the limit as x approaches 0 right here, you see how it's jumping back and forth so quick, really close to 0? It's not actually getting smaller or anything like that. So if it oscillates very quickly right there, then it definitely does not exist, but the equal sign should not be there again. Okay. What questions you got? We good?